appreciate you guys coming today. It's been fun to start learning about this sort of thing and understanding what the impact's going to be. As of 2 months ago, I didn't realize that satellites were on the brink of becoming such a widespread technology for us to use in the Internet of Things. So I'll go into that in a moment. I'm recording this. If it turns out okay, then the video will be up on my LinkedIn profile. The meetings that he's talking about, the third Friday events I've been hosting for the last 5 years, I've been recording those for the last 2 years. We have some incredible talent here in this North Texas area, and I've had the pleasure and privilege of having some of those folks come and speak. So go to my profile and you can see some of those links and presentations out there as well. There's also information about that on the IoT Texas Meetup site. IoT Texas Meetup gives a lot of information about various IoT meetings that are going on here in the North Texas area. So I got started this because my new boss, Eric Lennington, started a company, and he told me about 2 months ago, check into satellites because they're coming out with these nanosatellites, or launching these nanosatellites that can be used to enable IoT applications. See what's going on. His company would be an ecosystem player and a partner to these connectivity, the satellite connectivity guys. And what they do at his company, he's been 25 years in the telecom industry, created 5.9 software. When he went to stole his last company, started a new company, he realized there were not a lot of good tools in that area for creating applications. And so he took all the things he'd learned in the past, created an environment, a software development environment based on JavaScript, microservices. It's like Lego building your applications. And then you can quickly iterate them, create a commercial product in anybody's cloud, and then take it to market when it's finally at the point it needs to be. He wants to connect and work with these satellite guys to be able to do that. So that's what I've been doing. Google's awesome. These sites here are excellent places to go if you want to start learning more. And I'll get into more detail into some of the really good places to get started. So I'm going to talk about two different paths of technology development that have been going on with a little bit of overlap over the last 5 decades. And then they're all converging now to be able to give us capabilities and tools and things that we've never had before. So, of course, back in 1957, I was a young boy, and the satellite, the Russians, the Soviet Union, launched Sputnik 1. It scared the bejeevers out of us. As a nation, we've been flying over there with our U-2s, but they suddenly now had high ground. They were putting up Sputnik, and we didn't know what was in there. We didn't know what the implications were and what was coming next. We could watch it go over our U.S. cities. We could hear it beeping at us, sending its radio signal out to us. And we then created NASA. We tried to beat the Russians to get the first man, and Alan B. Shepard's awesome, but he didn't make it in time to be the first man in orbit. And then John Glenn followed after the Russians and whatnot. But we kept developing. What this spurred us to do was not only just go into space, it spurred and incentivized our various technologies, particularly electronics. So we began to get on the curve of exponential technologies and Moore's Law. And because of that, NASA bought a lot of chips and equipment from Fairchild. And that put them on the path to be able to create miniaturized, more powerful devices. So Moore's Law, of course, is every 2 years, the number of transistors go up. But the effect is the power doubles and the price goes in half. And so we went on that curve. It allowed us, along with other exponential technologies with launch capabilities, to be able to go into space and put up eventually lots of different satellites, the space shuttle, send probes to our various planets and send Voyager out of the solar system now, and then put up the International Space Station. And then we're on the brink of what's going to happen next. So to be able to launch all these heavy, expensive devices, we needed incredible launch vehicles, very small, very large size. And to be able to create the International Space Station, we had to send it up in different chunks and whatnot with these big rockets and whatnot. And we put them into, with the technology and the understanding we created, we could put these things into various orbits. We know about a lot of satellites that we've sent up are in geosynchronous or geostationary orbits. So they're basically rotating around the Earth at the same speed as the Earth, so they look like they're sitting out there at us. They're at 22,000 miles. That's a long way out there. A lot of other things, the International Space Station, the shuttle, and all operate in what they call LEO, low Earth orbit planes. And they can be circular, they can be elliptical, so they're called HEOs, H-E-O, highly elliptical orbits. They go in and out of LEO and then into other space, MEOs, medium space. So anyway, different ways to orbit around. And all kinds of equipment that we launched out there. We had to create, the Russians created a whole series of very powerful motors. We've created a whole lot of different things as well. Then other countries and enterprises have gotten into the game as well. So they're creating all kinds of rockets as well. But in 1999, this space exploration that we were on and the path we were on began to change. I'm going to talk more about this in a moment. This is something that was created by Cal Poly, California Polytechnic State University, and Stanford. And at first it was called a toy because it's only 4 inches, 3.9 actually, 10 meters by 10 centimeters cubed. And at that time, the things that could go in a space like that were very limited. But the idea was that it was going to give universities and the academia the ability to train their students and give people experience with putting something in a satellite that could be put on a larger, with a bigger load as a hitchhiker basically, and then launched up there. So a particular task could be accomplished for the university or the academic group. So the other path, I'm going to talk about for a second, was kind of parallel. The first example of the IoT, or machine-to-machine communications that we think of early days, was the telegraph. It was created in 1832, and Samuel Morse added Morse code to it. Now it became a mechanism that we could take and we can monitor from one location something that's happening at their end, and then use our intelligence to be able to just reply and send something back the other way. So it's been known by many different things, and of course we've called it telemetry, SCADA, industrial automation, telematics, and sensor networks, and many other names as well. We've used various technologies, wireline and microwave, private radio, Wi-Fi, conventional satellite, which is what I'm going to call the traditional large satellites, and then cellular, 2G, 3G, and LTE. So all those were the machine-to-machine communications until recently. Now, if you were going to look up the definition, it can be very convoluted, very complex. I boil it down. It's about remotely monitoring and maybe controlling something. And what we've done is add intelligence in every facet of the machine-to-machine and created an incredibly complex and capable Internet of Things system. But it's all boiled down to the fact that we're monitoring something and responding. So it's going to become the nervous system of the world, eventually, as we begin to sensorize more and more devices and objects out there. And it's going to take off. We're way down here in the curve, actually, even though I've been talking about this for 6.5 years, but we're beginning to see a lot of applications actually be put into effect in commercial operations starting on a very, beginning to get up to scale instead of being test systems. So if you look at the ecosystem for the IoT, it's an ecosystem play, but it's very complex. A lot of different levels, a lot of different expertise involved. But I boiled it down. We've got 3 areas in my mind. We've got devices and sensors, we've got some sort of connectivity, and then we've got the back end. Now each of those are rich in their own way because technology has been added to each of these things to make them capable of doing things that have never been possible before. In the back end, you got all the computer and applications and cloud and data analytics and all that kind of stuff. But I'm a wireless guy, so I've been focusing for the last 6.5 years and all my life on the wireless stuff. So networks were first started off with wireline, then moved to microwave, and then private radio, which is one of the first systems I put in at Motorola back in the 80s, private radio network for voice machine-to-machine. Then cellular 2G, still very popular around the world. We're moving away from that, going to LTE-M and NB-IoT. Of course, in the short-range stuff like Wi-Fi, Dash, and Zigbee and all are available. And then the conventional satellites. Now the thing about all of these things, they all have a place to play and they're useful, but each of them have a downside and a shortcoming. So cellular can be very expensive and power hungry. Wi-Fi is not very long range. If you try to build a mesh network, it may or may not work as you get it loaded. Private radio is not ubiquitous, and low power networks have their place, but they need to be backhauled and need to be able to reach at least the base station, the gateway, to be able to go out. I'm going to talk about that more in a moment because satellite may solve some of those problems and be a hybrid system. And then you got conventional satellites pre-Q. Now I mentioned a while ago, okay, so satellites, these large, beautiful satellites. A couple of problems with them particularly. They take as long as 5 to maybe sometimes 10 years from the time of conception to the time they were finally launched. So you have a long lead time. They're very complex to design and manufacture. And then once you put them in space, you may not be able to get back to them. Hubble's is an exception, and there's another couple of different things that we've gone up and repaired. But for the most part, you put it in space, if it breaks, it's done. It's just debris at that point. Now, there's many companies that have been in business since, at first it was the Soviet Union and the United States launching all these satellites, then other companies moved in through the 70s, 80s, and 90s. You heard about Iridium and Global Star, Orbcom and whatnot. These guys also provided some machine-to-machine capability. The problem is those offerings were very expensive. So if you, as a customer, were going to use one of their machine-to-machine connectivity offerings, it was going to cost you quite a lot of money. So your target, your project, or whatever you were monitoring, it had to be high value. And so it had to be worth the price to pay for that kind of stuff. And so people have been trying to figure out what's a better way to do this thing. So now this is where the CubeSats come in. When this CubeSat specification was first created in 1999, it was considered a toy by many professional technologists and satellite people at the time. They were saying, you can't do much with this. And for the next 15 years, it was only universities and academics that actually utilized this. It was a great training ground. It gave opportunity to put in one special thing into this form factor and then launch it as a hitchhiker on a larger payload that was going up. The ISS, the International Space Station, launched many things from their device, from their station, as well as other rockets that were launching things. You just shipped it out. Nice thing about this spec also, it evolved so that there was a pressure plate spring-loaded pad that would launch these multiple satellites that we wanted to have from multiple cubes, and it could be all packaged together and then just taken as a unit and put on the load. So it didn't have to be designed into the main transmission, main launch vehicle. Did you have a question?
Yeah. Where does it get its power? Is it solar panels, or does it stay forever?
Yeah, no, it's solar power. But solar power is the main way. If they use just a battery, then you only last so long. There's other exotic technologies that are being looked at, but this is probably the best way. You got all the sun. If you put your satellites into sun-synchronous orbit, in a polar orbit, you accomplish two things. One is the solar cells are always pointing at the sun and never get blocked out, so you don't have to worry about downtime. The other is, because it's in a polar orbit, it's going around, the Earth is rotating below it. So eventually, that one satellite's going to see all the world. But if you put a constellation up of maybe 150, 200 satellites, you'll be able to talk real time to every point on the Earth. Now, the other thing about LEO, low Earth orbits, they're between 100 miles and 1,200 miles above the Earth. That's the LEO space. Most of these satellites are going into between 300, 500, 300, 600 maybe miles in the air. So when you're that close to the ground, the good thing is your latency is almost nil. 22,000 miles, you have almost a half a second between the times you go up and down. At 300 miles, you're almost real time, but your beam, when you're transmitting down, you're only able to see a certain small part compared to the geos of the world. So this constellation makes up for that. You're able to see more and more of the world as your other satellites, either in the same orbit or in other inclinations, going around and covering the world out there.
So they form a mesh in space?
They can, and that's one of the other things that's happening right now. This is a tool that's going to enable innovation, and some of them are talking among themselves, so they create their mesh, and also talking to the GEO, who may use lasers with their high capacity to transmit down. So there's many different ideas that are being played with, because now it's becoming economically possible to do that sort of thing.
Wow.
It just blew my mind when I started reading about this stuff. I got more excited. So the conventional satellite guys are going to have competition, and that's where these CubeSats are going to enable companies to be able to compete. So instead of spending $500 million to launch your satellites, it's only going to cost $5 million, and the goal is to get it down to for a satellite, $600,000, 8 months. So if they accomplish that, you're going to be able to see an idea conceived, designed, manufactured, and launched within a year. Unbelievable. So this is an example of what the CubeSats look like. So a 1U cube is 10 centimeters by 10 centimeters, 3.9 inches cubed. You can stack those together. So the largest one is 12U in this picture. There's 24 U's and 27 U's that have been launched so far. So here's an example of 2 U's here. There's a single 1U up there. Here are the solar cells we were talking about. Now there's different arrays that you can put out there and different antenna configurations that you can put on these things as well. And if you wanted to take a look at the breakdown, you can see what can go into a microsat. The CubeSat specification has evolved over time, and some people have kind of deviated from it, but this will give you just a very good idea of what the basics are for building a CubeSat. So the term small sat is probably, or small satellite, is probably the generic term for anything under 500 kilograms. Anything above that is a medium, anything above 1,000 is a large satellite. So less than 500 kilograms, small satellite is just a good term to use for that. In that is CubeSats, NanoSats, and then all these other verifications. The small sats, CubeSats, and NanoSats term is kind of used interchangeably. So when somebody talks about any one of those, they're talking about something less than 500 kilograms. So this is what's happened. So in 2009, we had a small number of launches, and they were mostly for the academics to transmit up here. In 2014, though, that changed. Commercial operations began to realize they could use the exponential technologies, the Moore's Law, the miniaturized components, to put a lot more things into the CubeSats. And so they began to launch CubeSats directly for various applications, particularly IoT applications, but also for broadband. So two different ends of the spectrum. I'm going to talk about it in more in a second. SpaceX, OneWeb, Amazon are launching satellites. Some are cubes and small sats, and some are bigger satellites in low Earth orbits for high-speed, broad bandwidth communications for the world. On the other extreme are us, the IoT guys, who need small messages and our applications a lot of times are tolerant of latency. When we look at just the IoT applications, we're going to be launching. Blue is just IoT satellites. So in 2028, half of all launches are going to be for IoT small sats that will be launched out. And then the others will be for the standard mobile satellite systems that will be placed in orbit as well.
And let's just put the numbers right there. So you write 10,000, but in millions, so that's 10 billion?
Yes. Well,
Launch?
so 2028 is far out. Not probably
the closer ones.
They may have. This is in going to sky, so I didn't realize they were putting that as millions out there.
Probably not billions, right? In 2020, we're looking at a few thousand.
Yeah, because what I'll show you in another slide here in a moment. NSR talks about that in 2027, 6,500. I think it's 2026 maybe. 6,500 satellites will be in orbit, will be launched and whatnot. So,
okay, so
this is probably
not in
wrong
millions,
scale.
it's just units.
Yeah, maybe so something.
How long is the life on these? Do they stay up forever, or are they going to fall out of the sky?
I'll get to that, but the beauty of it is when you go into low Earth orbit, good news, bad news, right? Low Earth orbit, the Kármán line is at 62 miles. Anything above, anything below 100 miles will burn up very quickly within a year. Anything above that, you start having longer time that can stay in orbit. So 300 miles, you're looking at 6 to 10 years. At the 1,200 miles, you're looking at 25 years. Most of them are 300, 500, and the people launching and managing these CubeSats, small sats, are planning on replacing them in 3 to 5 years because Moore's Law. What they're doing now, in 4 years, will have doubled and doubled again. So you're going to be able to put more capabilities in your satellites and you refresh them. So there's going to be a constant re-upping of the technologies that are in these satellites. And then some of them are designed to deorbit. They'll have whatever left of their propulsion, they'll put themselves into an orientation that causes more drag to take them out. If not, there is a market and a industry that's developing that is launching satellites to go and collect this debris. But we're going to have to do that, and I'll show you why in a minute. Tom, did you have something? Okay.
It's great.
So, if you want to go and get started in understanding this a little bit better, go check out Doug Money's spaceitbridge.com. Spaceitbridge.com. This article popped up. He's been writing for 20 years on the topic of satellites and whatnot. Very clear and very good at his research and explanation. He pointed out that there's 18 companies as of June of last year that were launching small sats for IoT purposes. And since that time, even more companies have announced they're going to do it. There's over 1,600 satellites that will be put up here shortly.
Given the relatively short lifetime, 3 to 5 years, let's say, and the low orbit, what are the requirements for radiation resilience? Is it less than the 30K rad that is typically?
Absolutely, that's another good thing, because they're still within a lot of the shielding of the Earth's surface, Earth's atmosphere, and electromagnetic shield. When you start getting to 22,000 miles, you've got to really plan, because it's going to be getting radiation right out from the sun with no shielding and whatnot. But when you're in low Earth orbit like this, you don't have to have as much resilience and protection built into it. So these 18 companies are taking advantage of the CubeSat technology. Some of them are promising that the devices they're going to put and support out there, the end points, are going to be a couple of dollars a month. Some are even say a couple of dollars a year for you to be able to talk to these devices. Now, I haven't talked about this, but when you start, I did a little bit, but when you start putting these satellite constellations up in the various orientations and you're covering every place, terrestrial networks now only cover 10 to 20% of the Earth's surface. Only 10 to 20%. So you've got all these rural areas, even in the United States, cellular doesn't cover some of the places. You've got all the high seas and you've got all the polar regions. So you've got all these rural areas and remote areas that now can be covered economically. They could be covered before if you could afford it with these big satellites and the cost that they buy. So now we're starting to open up opportunities to be able to monitor and control things that were always out of our control and out of our vision.
Quick question.
Okay.
So can these satellites work within the LoRa architecture or the LPWAN structure?
Thank you for the setup. I will get to that in just a moment. Absolutely. Yeah. It's a hybrid sort of thing. And it's very exciting to see what
You paid me to ask that question.
These guys are great. NSR, Northern Sky Research, a lot of good information out there. They're saying it's going to be a $37 billion market here before long, 2027, and that there'll be 6,500 satellites. So whatever that scale was before, I don't know what they were talking about.
Millions.
But the point is, there's going to be a lot of useful satellites in low Earth orbit for us to choose from here shortly. The good news is, a lot of things to choose from. The bad news is, a lot of people are going to go out of business because there is so much competition in that space. But there's a lot of demand as well. So if you run your company right, you might be able to survive and make a profit on this whole thing. So some people have analyzed and said, at this point, we're at 23 billion devices, IoT devices in the field. And NSR is saying, or Statistica is saying, by 2025, there'll be 75 billion. So everybody's got these huge numbers out there. But in the past, I always worried that we wouldn't have the connectivity capabilities to do that. I'm beginning to think that we are responding with our technologies to be able to support those kind of huge numbers of devices. So it's exciting that we now have so many choices and possibilities to create solutions. So, it talks about the fact that LoRa and Sigfox have a limited scope because they can't go everywhere. They've got to have some way to backhaul and get it back. So these are the 18 companies that put up there. I'm going to talk for a moment about 4 or 5 of them. Astrocash, Fleet, Space Technologies, Hyper Global, Myriota. I'm going to save Swarm for the last because that's a fun one to talk about. So these guys, Myriota, this is an ecosystem play. And Myriota is just the satellite guys, but they've connected with Optus, who is also satellite for the conventional stuff, and networks out there. They've been running their systems for many, many years. So they're marrying up with Myriota to help add infrastructure and capabilities to the IoT satellite capabilities that Myriota is bringing. And you saw the antenna array there and the size of the device. So this is where he's talking about it'd be a couple of dollars per month, and then other people talk about a couple of dollars per year is what they're expecting. Myriota, their company came out of a research project that was at they're in Australia, and the research that was going on determined there was a gap between the ability of devices in the field in the remote areas to be able to talk up to something. And they realized Myriota, the researchers, had technology they could put into these cube satellites that would allow low power transmissions from the ground to the satellites. And the key that they also added, well, they got a lot of support. Boeing put in $15 million, as well as Myriota. The key technology that enables what they want to do, as the satellite comes over, the devices all transmit. They can see the signal that, oh, I'm in range. They tell the devices, or the devices have a timer. They know when that satellite will be above them. They all transmit at the same time. Myriota uses signal processing to decode all these signals to be able to get the information and still be low power. So if this all works as they're talking about, and it proves out, then it will be a very powerful way of being able to support devices in the field with long battery lives and relatively decent transmission speed, 20 kilobits to 1 megabits per second. You can do a lot of information transfer with that. So we'll have to wait and see, but obviously some people believe in them. If Boeing and all are investing in them. So that's what I just talked about. Many of these other companies are looking at partners as well. How can they expand into the ecosystem to support, give them support beyond just the connectivity that they're providing? Astrocast is out of Switzerland. They've got a lot of great engineering, a lot of great ideas. They believe that they can create a module that goes into the remote devices that the size of a credit card, very low power, and give them, if they put enough satellites in the constellation, they'll have very, very low latency to their devices. They're using L-band, which is 1 to 2 gigahertz, which is a good frequency band to use. The higher you get, the more moisture and clouds and rain affect your signals. You have more bandwidth, you can transmit more higher power and more information, but you got to contend with weather conditions the higher up you go. So L-band is a good one for them. One of the things that one of the things that they are going to do, though, they're not going to require GPS in the remote devices, which get expensive, power hungry, and cost. There are four GPS systems in the world. The US has one, Russia has one, China and the EU has one. And then there's 2 regional ones, India and I forget who the other ones. They take signals coming from these different devices, and the ground stations are actually looking at the GPS networks, these all 4 networks, and then determining with the power they have on the ground at their ground stations in these data centers, and analyze the signals and triangulate basically where these devices are. So you don't have to have GPS there. So that's their differentiator that they're talking about. Another company that's in this space is Hightower, and they're calling theirs, instead of low power wide area networks, they're low power global area networks, LP GANs. And they've one of the first ones to launch and get out there, and they're promoting the fact that they've got a lot of experience. They're out of the Netherlands, out of Amsterdam, and they've got a lot of good engineering and talent on their team. So we're keeping up with them. They're very, very interesting and very close to becoming, I think they got 3 satellites up right now, and we'll be launching more shortly, and they're very close to going commercial with what they've got right now for certain limited applications. So we're talking to them about doing that. They just earlier this month, again, talked to one of the possible partners out there and connected with Actility. And Actility is LoRaWAN capable. And so this will become a hybrid network, like you were talking about. So satellites can talk direct to devices In some cases, though, they're going to talk to the gateway for LoRa, and LoRa is becoming a very, very popular option to add to their satellite connectivity. And they're believing that their satellite modems will be 5% of what a conventional satellite modem would cost. So now you've suddenly reduced the cost. I didn't talk about this, but because the CubeSats are so small and lightweight, the mass is so small, you can put them and launch them into space for a very, very low price. You can either launch them as hitchhiking, their alternate or the loads. There's secondary loads on primary loads that are going up to the International Space Station or any other orbits, whatnot. So they are very low cost to be able to launch that way. Or there are a number of rocket companies that are called micro launchers that are designed just to put these CubeSats, small sats, into orbit. And so they're getting a lot of traction, and India is one of them. ISRO, India Space Research Organization, has got a great track record. They've been putting a lot of these satellites up in the air for the last couple of years or more. Vector is another one, and there's a third one. I have a slide later on. So there's more and more because the exponential times, all these different technologies are gaining in their power and whatnot. We're able to take advantage of them and create more powerful, low-cost technologies to use. So Hyber, one of the things that makes them different is that for their uplink, they're using 400 megahertz, not VHS, UHF frequency, 400 megahertz. I'm a radio guy, wireless with Motorola. 400 megahertz is awesome. 400 and VHF, very low frequencies, can go a long way at very low power. So if they can make that work and get the capacity that they need and keep their costs down, these guys could be a very big contender, particularly now they're marrying up with actility for certain applications using LoRa. Fleet space. So they're another one that is using LoRa as an adjunct and a hybrid to what they're doing. They talk down to the devices. So they've got a router, they call it the portal, that's on the ground on a pole, and it talks standard LoRa, not standard, but it's the LoRa that they're using, and 1,500 meters. So what is that, about 10 miles? And they can support up to 1,000 sensors to that portal. To that portal. The portal is using artificial intelligence at the edge. So inside of this router, it's going to look at the signals that it's got coming in and go, this information, I see it all the time, there's no shit different from anything else, I'm not going to send it up. This information, it needs to go up, I'm going to compress it. So it's going to be doing analysis and learning what it needs to do to optimize the interaction with these 1,000 sensors that are around it and whatnot. And then it'll talk to the satellite, which will then circle over a ground station and send the information back down then to a computer system, and then eventually to the customer. So, Swarm. So, I love these guys. They're out of Silicon Valley. They have what they call space bees. And instead of being the 1 U's, 10 by 10 by 10, they're 1/4 U's. So they're very, very small. Two problems. One problem, they put 3 of these on a launch vehicle last year and launched as a secondary load. They didn't get approval from the FCC. When the FCC found out about it, they said, time out, guys, you're in trouble, and threatened to shut them down and not let them launch ever again. Finally decided late last year to fine them $900,000. But because of the notoriety and because of the interest they generated in the technology, they've got some great technology and ideas and people behind this. Investors put in $28 million into the company. Swarm hired some high-powered people to make nice with the FCC and the ITU, which is the International Telecommunications Union that handles a lot of the other countries around the world. And so they believe they'll get approval before the end of 2019 to launch more satellites and work. They presently have experimental licenses to test out the satellites they've got and the satellites that they've launched since then. They've got 9 900,000, fine, somewhere along, yeah, 9 satellites in orbit now, and they're going to put 150 in orbit eventually to round out their constellation. The $28 million will cover the launch of all 150 of these satellites and the initial operating costs as they get up to speed and start making money. They are very aggressive and very interesting. I've had some conversations with them, and it's fun to talk to them. They are really on the edge of pushing it. They're Silicon Valley. So they're really pushing to try to make this a success and be innovative in the offering that they're providing. So their cost will be, because 1/4 U is even less expensive to launch than 1 U devices. And they oftentimes, in these payloads, they put multiple satellites in and launch them. I think the record was 103 that SpaceX launched here recently. And that may have been SpaceX satellites, but the point is, you can pack a lot of these things into the launchers and then put them out as you need to put them in space and be a relatively low cost. So now your operating cost or capital cost to create and launch is very low, so you can pass that saving on to the end users. And they're just like the other guys, they're going to plan on replacing their satellites every 3 to 5 years with more powerful satellites that can do more things. If and when they get approval from the FCC, then they're approved to work. We're particularly interested in Australia and New Zealand for some applications that we're looking for to do. So New Zealand said, FCC approves it, you're approved down here. And so some of theirs will be in polar orbits and cover that area down there. So more detail about how they use VHF frequencies. Again, UHF 400 megahertz, VHF I forget, I think it's 130 something is the megahertz range. Great range for the power you have to put into it, not affected by rain and moisture as much as the higher frequencies are. So they've got some great ideas. Let's see if they prove out. So there are a couple of challenges that these guys face. All satellite, our humanity, we actually going to be faced with some issues here. There's a thing called Kessler syndrome or Kessler effect. There was a NASA scientist back many years ago. He says, you know, if we put enough satellites up there and create enough debris, if they start hitting and creating more debris, it's going to be a domino effect and cascading. And eventually, we could create a world, a shield around the Earth, if you will, that you can't launch through to get to higher elevations or get to the moon and Mars and that kind of thing, because you will hit one of these pieces of debris, and after 17,000 miles per hour that you have to reach to get into orbit, then you'll destroy whatever ship that you're sending up. So there's been 900,000 satellites launched since 1957. 5,000 are still in orbit up there. I'm sorry, 5,000, yeah, still in orbit, but just shy of 2,000 are in operation. But you've got not only those satellites that are dead up there, but you've got a lot of debris from paint flecks, rocket engines, cowlings, different things that are falling off. They're also in orbit up there. So I didn't tell you a while ago, but Swarm, the reason why they got, one of the key reasons why they got fined and the FCC is not happy with them, when you're 1/4 U, NORAD can't track you. 1 U is big enough they can see and they can start plotting where you're going to be going and winding up and whatnot. 1/4 U, invisible. But, saving grace, Swarm thought ahead and put reflectors on these satellites, these 1/4 U satellites, so NORAD sees them as a 1/4 or bigger U satellite. And so that's only one of the only reasons, other than they had to really plead. They are getting back in the good graces of the FCC. But there's going to be a lot of stuff out there. So in addition to all the satellites we talked about earlier that are planned to be launched, 6,500 by 2027 according to NSR, we're looking at possible chipsats being sent up. Now these are even smaller than 1 U. A university student launched 105 of these, I believe, at one point, suborbital. So they didn't stay up at like 120 minutes or something like that in space. But they're invisible. They're invisible to NORAD's radar. And so if they start putting these into true LEOs and up there for a long time, what are we going to do about that? So they may have to have reflectors on them as well. Again, the fact that you don't have radiation hitting it like you would a higher orbit, they're able to put these things basically just like that up there in the sky. So an interesting thing that might happen in the near future. So we got 30 nano, there's actually 30 companies out there. Some of them are launching for other reasons, not IoT, but they're using the CubeSat to be able to monitor weather, to do mapping, to look at the seas and do research and that kind of thing. And then you got the IoT guys, the 18 plus guys that are out there as well. SpaceX, their Starlink program is going to have 12,000 sites, satellites in their constellation. Unbelievable, all in low Earth orbit. OneWeb is 650, Amazon Project Kuiper is 3,200 plus, and then NSR said there'll be 6,500 by 2027. So going to be a lot of stuff up there in the near future. The other challenge for the IoT satellite guys, or SIoT, satellite IoT guys, is all the competition that's going to be out there. Iridium came out, was one of the first companies to launch satellites out there for two-way communication, voice communications back, I forget now how long ago. They've renewed their constellation with 75 low Earth orbit satellites for $3 billion. They are old school, but they're going after this IoT marketplace. And so that's going to be another challenge for the startup IoT companies who are trying to get into this space. And they're just one of many.
Initially, it wasn't a commercial success, and then it was acquired out of bankruptcy, right? I mean,
Oh, absolutely. Iridium was way ahead of its time. The technologies weren't there to support it. The economics didn't work out. The military saved them because the military said it's strategic to our national defense, and that's what happened.
they almost let them just, go abandoned.
Yeah.
But it was meant for cellular communications, and they didn't anticipate that cellular coverage would get better so quickly, and that this would only be needed in very remote areas where there's not enough business to cover.
They thought the internet was just a fad. Yeah. So things are really amazing what's happening. Yeah. So that's pretty much it. If you got any questions, there's a lot of more detail here about things, but Jim?
I was just curious, and maybe I didn't understand it, but I didn't hear anything about how these little cubes position themselves. And I would assume that they've got to be oriented so that the right side points to the Earth or where it needs to, and they need to get into the right orbit and stuff like that. Am I
Yeah,
right or
so
wrong?
interesting, because there's a whole other presentation I can make on that. The propulsion systems that you can put into these CubeSats have to be limited because they're going on a lot of times, another load. And the restrictions for the loads that go on the primary launcher don't let you have hazardous materials. And a lot of these propulsion systems are based on hazardous explosive materials. So they have to come up with other ways sometimes. And I didn't get into a lot of detail, but they are looking at other gases and mechanisms to be able to help orient it, to be able to change its attitude, altitude. So there's a whole long list of things they're looking at to be able to do this. Some of them some satellites don't need to worry about tumbling. But most of them need to be able to orient to the ground so their antennas work properly. In that case, then they've got to come up with these other mechanisms to be able to have thrusters and to be able to position themselves and de-tumble, they call it. So that's a good point, and they're working on that right now. Tom?
The two questions. First is kind of like his. The ability to precisely position the satellite seems like you really don't have it because you're just kind of throwing it off as a secondary payload. And so does it really make a whole lot of difference exactly where it is? And the second question is, couldn't amateur satellites or have amateur satellites been able to put these up?
Oh, absolutely. When I said academia earlier, I didn't include, but a lot of amateurs put theirs up at the same time in the early days and now. So amateur radio, satellite amateur radio is very big in that space as well.
No, I mean amateur rockets.
The rocket industry is morphing, and companies are coming out focused just on being able to launch these micro nanosatellites. So I said about Vector. Who else did I have up here? So Vector, India Space Research Organization, very, very capable. And then Rocket Lab. They call their rocket electron rocket. And it's because I believe it's the pump that they use for helping the gases move through the combustion is all electronic. Anyway, they're claim to fame. What's interesting is they designed their rocket based on what they see the market need was out there, and their rocket is able to handle many of these small CubeSats at a very appropriate price, very economical price. They looked at what if they wanted to gain more market share, and what if they double the size of the rocket? How much more market share would they gather? They could do 62% with the size of the rocket they have now. So 62% works great. If they double the size of the rocket, they would get 64% of the market. So they stayed with this size here, and we'll use that. So so you've got 3 right there of companies that are focused on this, and you're going to have more coming out with I think call these micro launchers that are focused on this particular industry.
And how important is it, once you get it up there, that it goes to exactly the position that you want it, or it sounds like it's just kind of, it is where it is.
They do want them in the orbit that is planned so that you can track it one that the ground devices can know when they need to wake up. Some of these companies, what they're going to do is program the device on the ground to know when a satellite is going to be above it, because the footprint is relatively small. And so it's, to save battery, they want it to sleep most of the time and then wake up. So there's got to be some accuracy in this thing. I didn't study that very closely, at least not yet. But I think they're putting into orbits closer to what they really want and not just haphazardly. I'll check on that for the next time. Andrew?
So who's the main company right now that's launching these CubeSats? Like, who did Swarm use?
I think they actually used ISO for one, and they used a different company for the other one, and I don't remember. Because there is these companies, and Russia's big on launching this stuff as their secondary, and NASA as well with all their different rockets.
An approximate cost? I mean, I read, just quickly looking here, something like $40,000 for a cube. Is that?
Not yet. It depends on what part of it you're talking about. What I was reading earlier, to conceive and design, manufacture, and launch, they want to get down to $600,000.
Right, but just the launch. If you have the cube, to get it on the launch.
Yeah, I don't know the details of this, different parts. I just know that in 8 months, that was the thing. 600,000.
Can anybody launch? Are there laws? Are there?
Oh, there's lots of laws, lots of restrictions. So one, to be able to launch anything, you got to have that country's approval. To be able to go into space and operate over the United States, you have to have the FCC approval. Other countries, you have to use either ITU or that country's communications.
Okay, and then if you get it launched, do you have to can anybody have a satellite up there, or do you have to register it with a country?
That's a good point. There is no one coordinating body. So if you have approval from your country, you can launch.
So there's nobody stopping you from getting more and more satellites in this Kessler belt and all that kind of stuff?
Yes, and that's part of what's going on right now with these guys coming up with ways to go and pull the debris out of orbit. The impetus is to create some sort of central organization to track these things, to coordinate who's going to go into what orbit, and to be able to predict where they are and who's going to hit who. Because if they start hitting, we haven't created that ability to track and predict.
How do we not have this already?
Remember the movie Gravity? That was the premise of the movie.
I know.
Yeah.
How do we not have this?
So we were in for winter times. Yes?
Can you also comment on the kind of ground infrastructure requirements and stuff, like how many ground stations will be needed to connect those CubeSats to?
So I didn't get into that much, but some companies already have some infrastructure in place, either through partnerships or they've put the money in to create some of the ground stations out there. But that's going to be an important part if anybody needs to leave, go ahead and leave. I'm willing to stay here as long as you guys want to stay and talk, and we need to wrap up.
Yeah, I want,
But yeah, that's, every one of the companies has a different plan for doing ground stations and how they're going to support this. Once you get the information out of a satellite to the ground, then you can inject it into the internet, and then you can connect to whoever you need to. But that's a limiting factor in some of these cases because it's so early stage of what's going on. One last question?
Well,
Danielle?
I have a question, kind of go back to the trash and the debris about the implications of bringing that back on Earth or disposing it in some way.
It'll burn up.
So then what are they going up there to collect? Just to collect it and then
I didn't get to
centralize?
read, it was fascinating, I just happened to see it this morning,
Okay.
or midnight last night when I was working on this, that there are different techniques for being able to go and grab this stuff, and then it will be basically pulled into orbit and then burned up. Another way to do it is taking lasers from the ground, shooting them at these debris objects, and ablating them. So on one side where the laser hits, it will cause it to, one, burn off whatever material is there and make it more jagged and whatnot, and cause it maybe to start tumbling. When you can start changing its orientation like that, then it starts picking up more of the atmosphere, and then it will go in. Every one of these are at such a speed that they will burn up because of the speed and the amount, the density of the atmosphere they'll go through before they hit the ground.
So there's nothing residual that will make it back on Earth, or
They say nothing, everything will burn up.
they say?
So if it's big, if it was big enough, these are cubes, maybe 27, but you're still not talking about a huge object. And so the material can burn up. I think I'm done.
yeah, if ever.
Come up and talk to me if you want. If you want to get a copy of this video, give me your card or go check my LinkedIn website.
Okay, and if everyone could just join me in thanking Ed for a great presentation today.